Hi, and welcome to this third clip in this series where we are continuing our discussion of sodium oxide formation and the resultant Born-Haber cycle that we've drawn. This is from the previous clip where we've constructed this from the various definitions and processes that are underway in here. And what we're going to do in this question is essentially try to investigate and calculate, in this example, what the lattice enthalpy is. So the large arrow on the right hand side, and for the purposes of this we will assume that it is in the exothermic downhill direction. And so the question is wanting us to go from the gaseous ions all the way down to the solid sodium oxide ionic lattice and calculate the relative energy change, enthalpy change for that process. But using this Born-Haber cycle, we obviously can't go directly and calculate that, so we have to go via an indirect route, essentially in the same way as you would have done for a Hess cycle in year 12. And so if we take the same starting point, we have to go a process of going around the alternative route to ultimately end up at the same position and energetically evaluate all of those processes. And in order to do that, what we have to do is understand and know what the values for each of those individual steps are. And you would be given these in a question. And so if we to slowly work our way through the diagram and change the values as we go, we can establish that the delta HF value for the formation reaction here is a positive 416. These would all be in kilojoules per mole. And if we then continue to go around, the atomization of sodium is typically given somewhere in the region of 109. You sometimes see slight deviation in these depending on the questions. It might vary by 1 or 2 either side. Don't be surprised to see that. And likewise, we would insert the first ionization energy value for this. And for sodium, that is 494. These would obviously be positive values there. Incorrectly drawn a positive there. That should be a negative. So negative 416 followed by positive 109 and positive 494. If we insert now the atomization for the oxygen that we have there, we would use a value of 249. Inserting the first electron affinity, remember this value should be negative. And so for that one, that would be minus 141. And for the second electron affinity, remember, because we're inserting that electron into a negatively charged ion already, there's some repulsion there. And so we get a positive value, this time to the tune of 798. And so once we have calculated and inserted each of those values, we can ultimately calculate the question, which was to derive the lattice enthalpy value for this question for sodium oxide. And so what we need to do is put these numbers into a calculation that we can then solve using our calculator. So if we try to establish that the question is equal to the path followed by the orange arrow in the anti-clockwise direction, what we can see is that each of these arrows energetically will give us the value of each of the steps. So we have to travel in the opposite direction to the 798. And so we would change the sign of that and we would make that subtract the 798. Likewise, if we follow the steps going backwards, we would have to change the sign of the 141. So that will become negative minus 141. Obviously, we would then ultimately get a positive. We would then continue going downhill here this time. That 249 arrow is in the wrong direction, so we would subtract that value, subtract 249. The next step is also in the wrong direction, as is the subsequent one. So we would subtract the 494. But remember, we have to have a multiplication of 2 because we've got the 2 sodium ions and the 2 sodiums to atomize. So we would have that multiplied by 2. We would then subtract the 109 again multiplied by 2. And then the final arrow is going in the correct direction, so we would add that. Now we are adding a negative value, so ultimately we would still subtract it, but we would be adding that value to it, and we would then simply have to evaluate this answer by plugging these numbers into your calculator, and we would obtain an answer of minus 2,528 kilojoules per mole for this specific question, and the negative value would coincide with the expected downhill exothermic process. Typically the lattice enthalpy will be the largest value on your Born-Haber cycle, but with careful manipulation of the signs, being very careful of subtracting negative values and adding negative values, etc., you should be able to get those values underway. And if you were given a lattice enthalpy, to perhaps preempt a different type of question, if you were given the lattice enthalpy, you may be asked to find an unknown, and you would follow exactly the same process by inserting the values to all of the other values you have, leaving you with the one unknown value. And so for sodium oxide, that now completes that essentially 3-step process. We will look at another example in the next clip, and we'll do that in one go. So we'll see you in the next one for a further example, and thank you very much.